let's continue. And what I go this hour, and maybe some of you have already delved into this and seen this, is go into a very nice set of neural network models that is collected by this company Wolfram, the makers of Mathematica. They have a collection that's called the Wolfram Neural Net Repository of Neural Network Models. You find it by typing Google Wolfram Neural Net Repository. So let's have a look. And they collected a public resource that hosts an expanding collection of trained and untrained neural network models. And this is important, trained neural network models. So that means they have all the weights internally ready there. So this network model is performing like an expert exactly what it needs to do. It does classification, translation, face recognition, and so on. So you have a set of tools here that actually work. You can download them, put your image in there, put your vocabulary in there, or whatever. And these are the famous ones. You see we have age estimation, gender prediction, inception. Inception networks were these huge networks that works with these, identify main objects in images. Residual networks, ResNet 101, ResNet 152. And I go study with you in detail a couple of those networks, and there are quite a bunch. Feature extraction, about words, vectors. This is the face recognition net. We have colorful image colorizations from a black and white image, how to make a color image. All kind of translations, Monet to photo translation, photo to Cézanne translation. There are very interesting applications. What is so nice is that they have a download button. So suppose I look at this where's the big one? Suppose I look at this one, the Inception V3. It was released in 2015 by Google, and this model builds about previous Inception V1. This model achieves almost 80% top 1 and 94% top 5 accuracy on the ImageNet large-scale visual recognition challenge. You remember this challenge? There was 1.2 million images, 1,000 classes, and this is trained. You can download it. And there are buttons here. Download the example notebook or open it in the cloud. I downloaded this notebook already, and let's have a look. So this is what you get. You get a .nb file, and this is the notebook. I enable the dynamics. And you see a couple of... no. Come on, okay. First you see a research object that's actually the metadata of this network. So I download this, and now you get this network description. So you see it is a research object, and it has a lot of information inside. Click on plus. And now you see the descriptors. It's exactly the same as you have with, for example, you have an image. Suppose you have an image somewhere. Yesterday I was in a PhD defense, and one of my colleagues was giving a lecture, so you have an image like this. If you see this image and you look at properties, it's a JPEG image, and you see the details here. We have all these metadata, as I told you. So you see exactly the data where this picture was taken, what camera, and the same is for these networks. So you have a general idea. Every complex set has a very nice set of descriptors, what I call the metadata, and very well keep them together. It is what Mathematica does with the notion of image. Or you have the notion of a matrix with data. If you pull the pixels out, you only have the pixels. But the image structure has all the metadata. It knows the camera, the data, the geolocation, you name it. That's why you have these special processors. So you have also the same for net model. You load this model, but the net model also knows then also these metadata. It knows the task type, it knows the image domain, that's image. It has a UUID, it has a version number, and you need it to properly know what is this network exactly doing. So you have the command net model, and net model actually downloads the model if you don't have it on your computer yet. So you see a scroll bar running, and some models are big, over a few hundred megabytes, so you need some time to download them. And then you have these millions of weights in your computer. If you study this model in detail, you see exactly what Mathematica does. It gives you every layer. And from every layer, it is specified how big is it, what is it. This is a 3 tensor, and this is 3 by 224 by 224. So you input a small image here, and it is a triple, so this is a color image. And if you click on, let's say here, convolution layer, you get in the bottom all the information from this convolution layer. So you see there are 64 output channels. The kernel size is 7 by 7. The stride with which you step in the convolution is 2 by 2. Extremely detailed. If you collect, for example, you click on another layer, like this padding layer, you get information about this padding. If you talk about net graph layer, a net graph is a more complex structure in which you can build graphs. So net graph is a subset of layers in which you can have complex things. For example, you want to make a looping where you compare the original image with the processed image. You put it in a net graph. So, and this net graph you can dissect again. You see we have this ReLU layer, you have these convolution layers, and here you combine it, you sum it up, and you get an output. And Mathematica has very nice commands. And if you look in the help, you get you already did it, I guess, or I hope that you see what kind of commands are there. You can construct these layers. And these are now one-liners. So you can make a convolution layer. You can make a ReLU layer. You can make a fully connected layer, a softmax layer, you name it. Suppose I subtract, let's delete all the output. Let's make it a little bit bigger. So net is now my model, and that's a very big thing in memory. It may be several hundred megabytes. You need some bigger computer, but most of us have this now. And you say, okay, let's extract from the net the first one. And I want to see the weights. So I call them weights 1, the weights of thing. And now weights is extracted. I put a semicolon here so I don't see it. So what is the dimensions of these weights? Okay, 64 by 3 by 7 by 7. It makes sense. It already said in the metadata that they have 64 filters. And these filters are color filters, and they are each 7 by 7. So can I see them? Because that makes sense. Can I see the filters that the thing has learned? So what I like to do is transpose this into 64 sets that are 7 by 7, 3, because the triples should be in the end. So I do a transpose, which I change the order. I make them now 1 and then 4, 2, 3. So I put this number 3. The 64 I keep at the front. Then I want this number at the end. This 3 goes that comes on place 4. Now I have 64 items that are 7 by 7 by 3. And if I just say display them, so put in front of each of them, so this is now a function. Weight is a whole series of 64 images. This is the function map. So I have now a function that says, put image in front of it, so it makes from this small matrix an image. Image adjust means scale the image, so find the minimum and the maximum and put that in the range from 0 to 1, and then display it. And these are the filters learned. And now, after this course, they make much more sense. This is very interesting. So what you see now are all these filters we talked about in the course. So you see filters that are the red-green filters. You have here the first derivative filter. You have a second derivative filter. It's very noisy. This is only 7 by 7. And what is really interesting for you to see is take some networks. You can download them now. See what they have learned. How is the internal stage? You can also see what does the second stage learn, what does the third stage learn. So you can dissect these trained networks and see what they do. Well, because I give in this course you a whole background in what is the first stage doing, it extracts geometry. It wants to find the local structure. And what is structure? We need the mathematics for structure. That's differential geometry. We not only need edges, we need the whole Taylor expansion. We need the local descriptor of this very local patch. And now every patch is described by this whole vector. So I have 64 measures in this one pixel. Now I need to combine pixels into perceptual grouping. So I'm not comparing intensities anymore. I'm not going to look at what is the intensity difference with my neighbor. No, what is my tensor difference? So it gets more complex. But that's exactly what happens in these neural networks. And vision cannot live with intensities alone. It's far too limited. So in the visual cortex, it explodes the whole thing. Every pixel gets enriched by a cortical column. That's why we have cortical columns. It's the representation with all these guys. So a cortical column and a tensor is the same. So if we study in these visual systems, what do these columns do? Well, these columns are organized in a very nice orientation way. So orientation must be a very, very strong perceptual grouping item. So that means orientation, if I have a line here and a line there, yeah, of course, they're very much oriented. They are not related. They are not related, but they are related. So this sub-Riemannian stuff is an attempt to get this orientation into, can I go to perceptual grouping in layer 2 and in layer 3? But this is what layer 1 is doing, and you see it is, and one of the things I want you to do in the exam task is, we look now here at the eigenvectors. You remember these long eigenvectors? You chop them up in eigenpatches. These eigenpatches are the filters. But there's also eigenvalues. And eigenvalues means what is the relative proportion that this filter is contributing. You had this ranking in eigenvalues. They quickly decrease. Only the first ones were important. Well, have a look at these first ones. So have a look at what do these, what is the ranking, what are the weights? Some of these may be completely irrelevant because they're with very minor eigenvalues and they do not describe the image actually. I think that max pooling that we do is pretty rough and pretty ad hoc. You want to have the most descriptors ones, so people say, okay, take the maximum. I think take the first eigenvalues. So take a very limited set. The eigenvalues are only 3 or 4, so take that as a data reduction step. Then you hardly lose anything. You don't do this ad hoc. It's very well mathematically described, but then you have to do an analysis. And one of the tasks in the exam is have a look at these relative weighting of these filters. So you also see that these are the steerable filters, so they come in different orientations. You remember that we saw that this guy is a first-order derivative filter, and it comes here with, well, this is the y derivative, and this is the x derivative, and this is exactly the steerable pair for this first order. A little bit noisy, but you see the idea. How can you use an image like this? Very simple. You have the net model, and you make it a function working on something. So behind the net model, you just say, open square bracket, close bracket, and you put an image in there. And this was a classifier, with 1,000 outputs. So it gives you which of these 1,000 outputs is it. So you just let the net model run, and it finds peacock. This is now an operational classifier you have on your laptop. It works. You can put in any image you like, and it recognizes for you. So you don't have to build it anymore. You can just use it, and you have the full code. You have the full operational weighted network. It's trained. It is operational. It's an entity object in Mathematica. You can ask what is the... so this means it is the net model. And Mathematica knows much more about these objects because it is connected to Wolfram Alpha. We all know Wolfram Alpha. It's an extreme database where you can type in everything and you get lots of information. So this is a male, p-fold, etc. And if you ask for the properties, well, this is a little bit about specific Mathematica. But let's see if we can get some other. If you type the help from net model, you will see that you can interrogate this net model in many ways. You can ask for the separate layers. You can ask what are the weights in the layers. If you output this 1,000 probabilities, show me those probabilities. In this case, show me the top 10 probabilities. And then you see, well, peacock is probability 1. Indigo bunting was very, very small. So in this case, it was extremely clear that it was a peacock. Sometimes you get 50% that, 50% that, and then, of course, it's not really doing a good job. It's very nice to test this on your own data and play with what happens. What I never did before, you can rotate this image 180 degrees and see if you still recognize it. We were not so good in face recognition. Well, play with it yourself. You have now the tools to actually do it. I think this guy will recognize the peacock because it's more or less rotation independent. It looks at all the feathers, and that's what it does. If it is not in these ImageNet classes, it does a bad job. So if I put in something here it has never learned, let's see what the network is doing. It gives a buckle, but that's not really working. If you want to have the names of all the available classes, it downloads now all these names, and you see here, this is what it all has, and you can, so all these items were in there, but the lesson here is, it's completely interrogable. It's completely, you can question everything from the network, you can, up to the smallest detail, you can see what does it, what has been learned, what are probabilities, what happens in my image. So that's quite nice. If you remove the last layers of the net, and you do that by, you just say take all the layers except of the last -4, so that means kick out the last ones. So it is just a take command in Mathematica from the net model. The net model is a list of these layers. You just take the first layers minus the last 3 and the output 1. So now we have a limited set, and now it's still a long network. You can see what's in the network. But on the end are now a couple of things are left. And now get a couple of images. So you say images is this whole set. And we have cats and dogs in these images. I don't know, about 20 of these images. And you can play with images yourself. And this set was called images. So I run it. And now I want to have a feature space plot of these images. That means it takes classical features and it makes a kind of a, this is the first and the second largest plotted in a space. And you see that there are already, there's a distinction that the dogs are in the bottom and the cats are in the top. So there's already a first split. But now we extract the weights from this net. We look at the dimensions. Well, it's the same as what I did before. Actually, we see now the things. And this is interesting. We can do transfer learning. You all know what is transfer learning? It's very famous, and it is extremely simple, because what you say, if you train a network, very often you see that the first stages in this training are more or less the same. I have them. And we know that the very first one is the basic set of these, what we get eigenvalues from these patches. So you use a trained network and tell apart images from new things. So you name a training set. A training set is different. You say, I have an image and a label. And a label is easily, that's an assignment, an association in Mathematica, and the simple thing is just an arrow. This means it's a cat with the label cat. And I have a trained set. It's pretty small. It has some cats and it has some dogs, but they have two labels, and one of the labels is cat, and the other label is dog. The test set is to validate, to see, is the network that I learned giving this? I know the ground truth, so this is the ground truth. You remove the linear layer from this pre-trained net. So I get now this big layer again, 27 layers. And now I make a new net composed of this pre-trained net. So I use this whole net. This is, all the weights are in there. It's pre-trained. It's fully knowing what these levels do. And I add a linear layer and a softmax layer. And this is the way how you do that. There is a command net decoder. And net decoder is actually a simple program that makes the images compatible with what the program demands. So if the resolution is not right, it makes the resolution right. If the representation is different, if it is for a black and white image and it requires a color image, it just makes the color RGB, but then all the RGBs have the same value, then it's a gray value. So if you have 17,17,17, it's a light gray pixel. So net decoder does that forward and output, so it does also in the output. So now I have this network, but this network is, as you see, it is not initialized. And we need to learn this network with the images that I just said. So how do we learn the network? That's a very powerful command. It's called net train. And net train is doing backpropagation. So it takes an image, feeds it forward in your network, you measure the error, and then you get some cross-correlation error, you adjust the weights, and you do it again with the next image. So net train is the command that can take a long time, depends on your computer. Mathematica fully automatically sees how many cores you have in your CPU or how many cores you have in your GPU, so it automatically divides the task. It's quite powerful. Of course, the same you can do in many languages. You can do this in all the other ones, in TensorFlow. But the Mathematica, it's particularly easy. You say net train. It's very few images now, so it is relatively going fast. But it shows you the progress. So it has a progress bar. It's using the Adam optimizer. I have a whole bunch of GPUs. I can show what my computer is doing. So if I look at performance, I have a resource monitor. And here you see all my, I have eight GPUs. It's probably ready. I'm not sure. Anyway, you can see this on your own computer, and I was hoping to see full-blown use of it. I've seen that. But okay, so now we have the trained net. So untrained is gone. We use net train. It's no longer writing here untrained net. And we can see how accurate is it. So we put in the test set, and it is really accurate. You can ask all kinds of parameters, the element array counts. Well, this you can do yourself, how many counts are in this network. This is a huge network, 7 million of connections. So this net train had to do a lot of updates. we saw in detail what backpropagation was doing. You remember the numerical example? Well, this happens in all these GPU-based calculations, but then, yeah, finally for hundreds of thousands of images. The layer type counts, so how many layers are there? In this case, there are 57 convolution layers, element-wise layers, padding layers, so it has a lot of, and this is the summary graphic. And that's a very long set of, let's say, overview of what the network is doing. You can export the net in a special format. It's called MXNet. And then you can share your network with other research groups that do the same thing. OK, network number 1. I want to go to another network. And that network is related to face recognition. So let's go to the course. So we have here the open face recognition. I enable the dynamics. It has a big title. No, come on. Make it bigger. So this is trained on the Casia web face and face script data. If you look at the Casia website, the Casia web face, you can find the download things here. I downloaded this. It's quite big, and I think it was. I have the Casia website here. I have them here, Casia faces. So it is a 4 GB zip file. You download these faces, and here's the directory. And every directory is a person. So I click a random one. And now you get images from all different periods also from this person. And it's quite interesting. They are very variable. In this case, with lots of hairs and sunglasses, different situations, black and white. So it's in the wild, more or less. Probably taken from a picture album, not in a studio, front face, all the same, more difficult. You see there are different shadows and not frontal. A very interesting database. So this was trained on it. We close it. So we load the metadata. Let me delete the output. And see what it is. It's a neural net. Represents a facial image as a vector. Well, we saw it before. We had these 128 numbers, and we could see, can we see that as a vector? So we download the net model. In this case, it should be already on my computer. Otherwise, you see a download button and take some time. And it's 26 layers, and it has the regular thing that it has a batch normalization layer. Ramp means the ReLU, that's the rectifying linear unit, so no negatives, only positive. The pooling layer, that could be max pooling or mean pooling. Convolution layer. And now what we see is train the network, or let the network get the features. So it is supposed to get the features from this face. So I have now these features. I call them features, and I put a semicolon here so I don't see them. So I ask it again. And these are the features. Not so interesting, but just 128 numbers. How long is it? 128. And now you take a whole random set of faces. You call it a batch. You set a whole set of faces. And the Mathematica is so nice, you see what you do. You put the faces literally in there. Because it's a very symbolic language, you can put anything in there. You could A, B, or the number 7, but you could also put an image in there. And comma, image that. And that's, I like this a lot, because this makes life for me. This program is made for humans, not for computers. So I have my badge. I immediately see, because I'm a visual machine, my whole brain is for visual, so I see this much better than the name of some long directory path. That's not what I'm made for. I'm made for images. So if we have this, we load this, we collect from all these images now these features. So let's see what is the dimension. I had 72 images. Every image I have 128 features. And now you can visualize these faces and see how do they group, how do they look in a feature space. And this is more or less the feature space. And it has the first principal main descriptive components. Is there some interesting grouping? Not really good to see. If you have images that are very similar, people that have the same, so this should be probably the same guy. This should probably be the same guy. It would be strange if you have a woman and a man here together, because they might have. So you can do some studies here, visualizing how well are my features descriptive. Maybe you need a 3D feature plot space. So Mathematica has a command, feature plot space in 3D. And the more you take, what you really want is 128 dimensions. You cannot visualize them, but you can do this in 3D. Well, here you have it in 3D, and of course you can pick it up and rotate the whole thing. And now you can study, is there any grouping in 3D? I'm just telling you that there are fantastic tools to study your network in terms of how well do they perform. This set of images is probably too small, and you don't see particular grouping yet, but the way you can analyze it is very visual and it's very interactive, and I just show you the tools that you have things here that other programs do not so easily give. If you want the nearest nature, the feature nearest, and then it looks in the 128th dimensional space, then you could say, okay, I take from this whole set of faces, I want from this image the nearest faces. So it finds now the nearest faces. No, it's not really a good job, I find. And this is again the same. You can measure all the how many elements are there. So incredible long lists. These are all the biases. How many total element counts are in this? 3.5 million. So this is more or less the same. Okay, this was now the 128 features. It gets more interesting if we look at these points on an image. You remember, we could pick these points. We have it right here. I load the research object. I download the model and install it. It's called 2D face alignment, net trained on 3000W large post data. Let's delete the output. So we want to get these very special points that are learned, and we learned these 68 specific points on the contour of a face, around the nose, in the eyes. And if you input this net model with a face, it gives you what's called a heat map. And a heat map is a visualization of a probability over 2D. So it is now looking at these images. It's a quite large network. But it should be faster. What happens? Oh, it's done. Oh, it is because it generated this lots of output. I should have had here a semicolon. The generation of these, I don't know, thousands of things is taking the time. So let's look at the dimensions of these heat maps. 86 outputs of 64 by 64 filters. So what is the first filter actually then learning, or what the output filter learning? So you do a matrix plot, which you map on all these heat maps, not all of one, but I take number 1, 12, and 29, just random ones. And how does a heat map look like? Well, this is a heat map of a particular feature point, the probability, it is right there. And you can do this from all these 68. What is the probability that that point is found there? And you find these probability maps. How do you really find the feature point? Well, take the maximum in this heat map, because that's the highest probability. So you can do this. Actually, this is a function that maps, that picks the maximum position of each heat maps and returns a list of landmark positions. So we call that net evaluation. That's actually take all these probability images and give me then these points for all the heat maps. So this is a little bit of a loop that does that. It does it quite fancy with quotient remainders and so on. So don't worry about it. It takes the maximum. So let's take a phase. And now we take the maxima of these. And here we have these locations. You see these are doubles, so pairs. So we map the function point on these landmarks. So we put points in front of everyone, so we get location of this kind, and we put it in the graphics. And now we see these are the locations, and we clearly see a phase. So if we take groups, and this has already 1 to 17 is the jaw, 18 to 20 is one eye, and these different groups, you can give them different colors. And let's visualize these different ones. And now you see we nicely get the network tracks the contours of this phase. And you can do this for any phase. So now we have the pose of the phase. We can study these points if the phase is moving, if the phase is talking, if the phase is nodding. So we can very carefully use this net to do statistical shape analysis or all kinds of, you can recognize phases by registering them. If a phase is looking like this and you want it like that, you do an affine transformation on these points. So it's relatively easy. You don't have to do this on these millions of pixels. You do it on the extracted points. So this notebook network that you have here with all the weights is a trained expert doing that, right available for you. And you have now about 50 of these notebooks, and you can play with it. It's fantastic to do during Christmas if you have nothing to do. You take a network and you play with those things. I go play a little bit with this in the next minutes. If you have images like this, images of the wild, there are two phases, and the network will not work on an image like this. So you first need to find the phases. Well, happily, there's a lot of software that finds a phase. And there is a command here that's called find phases. And this little subroutine writes, of this little routine writes find facial landmarks. It uses this find faces, it trims then the image and gives you back this image. So if I load this image, I define this function and now run this function on the image, find the facial landmarks. So it has cropped, you see, it has cropped the particular face, the pixels from the image, and it finds all the landmarks. It has cropped the second image, and it has found the landmarks. So this is an extremely powerful tool to play with faces. You can do this on your own pictures, take your camera. You can even do it interactive, take your webcam and take an image, let the thing do it, and in the meantime, move, update it. It's a fantastic, insightful thing. And now you visualize the landmarks, and you see that on the faces, you can now visualize these landmarks. But the ease with which you can do this, that's what I really like. This is a very educational tool. Play with deep neural networks in the way you like to play. So in this network, you can see what happens in the different layers. Read out the weights. See what I leave out. You can say, I make the whole network shorter. So lots of experiments are now can be done. What I also like you to look at, and that's one of the questions in the exam, look at robustness. And we all know what is robustness. Is it still working if the input is garbage? Or the input is not so right? So I'm not giving it a face, but I give it the whole person. And this person is a lot of background, there's a lot of hair, there's a lot of clothing. So now I take an image, and I do not the cropping, where you can do some cropping at different sizes. So we make different crops. We have the crop of the face with more hair around it, and you see more and more of the body. So how long is it still working? What is the stability? What is the robustness of this? So I take these 4 images, and now see what the points do. So one by one. And on the first one, I expect it to be pretty right. And then I don't know what happens. So let's see what's happened. It's now running in multiple times for every image. These images are quite large. You see here net evaluation, so it does it one by one. It should come in a few minutes. Did I forget something? No, I loaded everything. Okay, here we go. Well, it finds the eyes, the nose, a little bit white here. And now you see it begins to go wrong here. So this is no longer, and here more and more you see, and here it completely goes wrong. So if the input is not similar to what it has learned, it doesn't make sense. So it only works on the data that you have input there. So, but we all know that you need to train it with the data that you see. I was never trained with Chinese characters, so I don't recognize them. It's as simple as that. But these experiments are nice to do, and of course you can ask the whole set of how big is this network. It's 23 million weights. That's pretty impressive. So if you update this, you need quite a lot of faces to do that. But we have 10,000 of faces. That's exactly what happened. But for you to train this takes months. You have it already trained, you download it in a fully trained sense. So you have the 23 million weights. You can just go ahead with a fully trained network. What I like you to do is an example I give here. And then we should think of time. That's my last example. I have a lot more things here. But suppose you look at this movie. This guy is looking at his points, and he is moving himself around. And you see, because he's moving, there's a lot of shape variation here. It turns out, if you use all these coordinates, and you put these coordinates in a long column vector, so you get x, y, x, y, x, y, from all these points, and from all these different faces, you get all these, from all these different frames from this movie, you get these column vectors, you get a matrix, you can do PCA, and you can see what is the first eigenvector that is the main variation in that phase. So you can see the mean plus or minus that first eigenvector gives me the first main variation. The mean plus lambda times the second eigenvector gives me the second variation. So you could see if I take a lot of points from these images, and I do a lot of things, and you see, okay, the first main variation was this one. I did mostly did. And the second one was in another way. So I can dissect variation in a more complex way. A guy who did that it's called active shape models. And there are beautiful papers on active shape models. This is the first mode, the second mode, and the third mode. And you see the variation in these faces, how they vary. So now for the first time you see, okay, what are variations in a shape actually? These eigenmodes give you the variations of a shape. So if you have lots of faces, suppose you have a whole range of, what's actually varying in all these faces? Well, if you study what this face is doing, the first variation is, I see it from different angles. Okay, so that's the most varying thing in these natural images. Or I see it from up and down. And the second, his eyebrows are going up and down. So that's another variation in the face. I want you to do this on faces that you record. You take your smartphone, you take a movie of your face, and you do something. You extract all these points, and you do these principal component analysis. It's very simple. I even give you a notebook that does this, and then we go... it's called point distribution models. Describing shape variation. And we do exactly the same as with these patches. So we use principal component analysis. This is an extremely powerful tool, and I think it has a lot of applications in understanding what's the brain actually doing. The brain is not storing a million of faces. The brain is storing these eigenmodes, and it can combine lots of these in simpler faces. So what I do is I calculate not the variance. You know all the variance, that is x minus the mean, and then how much is it? So you take lots of them, but now I take pairs. So I have an xj, an xi, and an xj. And this is what's called the covariance matrix. Do you all know what is a covariance matrix? Otherwise, look it up. It is a very basic statistical thing that you learned in the first year. But you have to know what it is. It's actually how much is, if I have a lot of data, how much is every aspect of this data varying relative to each other. So, well, this covariance matrix, you can make a matrix. It's a matrix, it's a square matrix. You can do principal component analysis, and then you get eigenvectors. And if you take the mean plus or minus these eigenvectors, you get the variation. Let's actually do it. I set some options. I kick out the output. And I make some points that are on a circle. So I make pairs, and they have cosine phi and sine phi. And I make 36 of these pairs. And then I'm going to change a little bit randomly. It's a circle, and I'm going to change randomly the position of these points. I have 25 representations. Let's look at these representations. I look at it as a movie, and you see this is my movie. It's expanding a little bit, and it's random. So my main variation is it gets wider. But I have a lot of noise because I have all these points. But it's 25 points, a very simple set. I have a number of frames. So what I do now is I say, flatten the data, so make them into long column vectors. So now I have 25 column vectors of 72. Take the mean. Well, here we have these 25 means. If you plot the mean, you see, okay, this is the mean, all the noise is gone. Now I calculate the covariance matrix, and the Mathematica is, of course, extremely simple, covariance of this matrix. So what is the dimensions? It's square, 72 by 72. And what are the eigenvectors? Okay, calculate eigenvectors. 72 eigenvectors, each 72 long. And now I go show the first eigenvector. So I say here, this is the mean, mu, plus some weight times the first eigenvector. And W I let run from -1 to +1. So I add negative, 0, positive. I add more or less a little bit of the first eigenvector to the mean. So this is what it's all about, mean, mu, and show this as a movie. Now you see the first eigenvector variation, and it's exactly what I expect. This is the main variation of this dataset. So with these very few commands, you can now see the main variation of your face, or any point. Take your hand and move it like this. So if you want to design a deep neural network for, let's say, sign language, what would you do? Find specific points on your hand and see if you can do the sign language things. It is exactly what happens here. So you can see what are the major variations. If you study the second mode, well, this is the second mode. There is no second mode, it's noise. The main variation was that it gets wider. And you can do this from these faces as well. So, leaving this, I have a few more, but that's more appetizers for you because we have a few minutes left. I go back to my website. These are these Wolfram neural nets. A few of them are really nice, and this afternoon you should have a look at what they do. For example, you have here the photo to Van Gogh translation. It's a network, you download it and you put in your own photo, but here you can see what it is doing. You load the metadata, you load the model. It's quite a big model. And this model has learned Van Gogh images and has learned what is typical in Van Gogh images. What are the textures, the colors, the color derivatives, and so on, what is specific. And then it says, if you now change edges that you find in a regular image by Van Gogh edges, Van Gogh had the typical use of this, he used specifically, let's say, yellow and so on, you can make from this image a Van Gogh image. So it looks a little silly, but it is exactly, it has learned any relation, and you can make lots and lots of relations. So play with those things, but my thing is, do not use this as an application like everybody does, but use it for what happens under the hood. What can I see that this first layer is doing, the second layer is doing, and see what feature combinations are being made. That's the structure of this course. Not how to use it. There are lots of courses and fun and haha, and put it in your Facebook, and it is make it of your face. But that's at the 0 level. And the last one I want to show is, sorry, I clicked it away. I think I showed it before, but anyway, there are 50 of them. So this one is age estimation. What you do is you train thousands of images with a number, what's the age? And then for you to find out what are the specific things that makes you old. So why do you have this age? Why people have wrinkles and so on. So it is much more, other than fun, you can download it, it's a whole network. So you put in a face, and even if this face is partly covered by hands, it finds different probabilities, but here, what does it say? This guy is 18 years old. If you put my image in there, you get 65 years old. Well, I'm just retired. I'm now 67, so it is more or less good. And put in your own image, and you will see that even if you have glasses, you have a beard, or you have bald, it doesn't matter. It finds pretty good. So it looks at facial features, and for you to find out a little bit what might these facial features are. And of course, big companies like Dior, etc., they sell millions of ladies who want to get rid of wrinkles and so on. They know now exactly what makes people young. Well, not the wrinkles, but I don't know, maybe the flapping of this, whatever. But people look at incredibly detailed now. Deep learning gives them the features, what makes people older. So here's the distribution. It gets lots of probabilities. And you can even first get an image out. So you do the face cropping again. So use find faces. This is the Pope. And you see he's 70 years old. It's fun, but the fun is really, you have now a tool that you can look inside. What are the filters doing? What are the probabilities? So use this tool as a play tool. This afternoon, the tasks is look at these networks and see how you can explore them. They have a lot of information about robustness, about extracting the first layer, It's very insightful given the rest of what we learned this week. You see, differential structure in color. You see differential color. You see the steerability. You recognize many things. You see the robustness. You can also start already with the exam tasks. Have a look. And what I will do tomorrow is give a full overview of the course again. So we really summarize the whole thing. We give the big picture. And at the end, we have the last hour left for questions. So if you have questions, it's the last time you see me. I hope you see me more after that. Then the course will be ended and you're left alone. So if you have questions, give them tomorrow. But tomorrow I give a grand rehearsal of what we have seen so far. So we start with the first layers, and then we just let it all fall down, make the picture whole. Any questions now? Hungry? Lunch? Let's go for lunch and experiment this afternoon, and see you tomorrow and this afternoon. Thanks.